To understand a camera, we first have to understand that we don't see objects. We see reflected light. Every object reflects photons in a chaotic, scattered mess. A camera's job is to take that chaos and organize it into a coherent image. It does this through three distinct stages: refraction, regulation, and conversion. 2. Stage 1. Optical refraction, the lens. The journey begins with the lens. A camera lens isn't just one piece of glass, it's a series of elements. Refraction. As light passes from the air into the glass, it slows down and bends. This is refraction. Convergence. The lens elements are specifically curved to bend those scattered rays toward a single focal point. Focusing. When you focus a camera, you are physically moving these glass elements closer to or further from the sensor to ensure that the focal point lands perfectly on the sensor plane. If the point lands in front of or behind the sensor, your image is out of focus. 3. Stage 2. Regulation, the exposure triangle. Once the light is focused, the camera must regulate how much of it reaches the brain. This is managed by two mechanical gates. The aperture. Located inside the lens, this is a ring of overlapping blades. We measure this in f-stops. A lower f-stop, like f1.8, means a wider opening, which not only lets in more light, but also creates a shallow depth of field where the background is blurred. The shutter. This is a mechanical curtain. It determines the duration of exposure. A fast shutter speed, 1/4000th of a second, freezes motion by denying light any time to move across the sensor. A slow shutter speed allows light to paint across the sensor, creating motion blur. 4. Stage 3. Digital conversion, the sensor and processor. This is the most complex part of the process. The light finally hits the image sensor, usually a CMOS chip. Photodiodes. The sensor is a grid of millions of tiny photodiodes. When a photon hits a photodiode, it knocks electrons loose, creating an electrical charge. The more light, the stronger the charge. The Bayer filter. Sensors are naturally monochromatic. They only see brightness, not color. To fix this, we place a Bayer filter over the sensor. This is a mosaic of red, green, and blue filters. Because the human eye is more sensitive to green, the grid actually uses 2 green pixels for every 1 red and blue. Interpolation. The camera's internal processor then looks at this mosaic and guesses the true color of each pixel by looking at its neighbors. This math is called demosaicing. It then compresses this data into a format like a JPEG or a RAW file. V. Conclusion, the final output. In summary, the lens organizes the light, the aperture and shutter regulate its volume and timing, and the sensor translates that physical energy into a digital language of ones and zeros. Every time you click the shutter, you are witnessing a perfect harmony of mechanical engineering, optical physics, and advanced mathematics. Thank you.